Imagine you have an n by n chessboard and you want to put n queens on it so that no queen can capture another. A queen can move any number of squares horizontally, vertically, or diagonally. The problem is to find a way to place the queens so that none share a row, a column, or a diagonal. This is like trying to seat n friends at a round table where each friend must sit far enough away that they cannot shout to each other. We need a rule that tells us when two seats are too close. The intuition is that we are looking for a pattern that avoids clashes, and we will search for it step by step, trying one queen at a time. Think of every possible way to put queens on the board as a huge family tree. The root of the tree is an empty board. Each level of the tree adds one more queen, choosing a column for the next row. A node at depth k represents a board where the first k rows already have queens placed. The children of that node are all the safe columns we could put the next queen in. This tree is called the state space because each node is a state of the puzzle. Building the tree is like drawing a map of all routes you could take while walking through a maze. Each branch is a decision. Each leaf is a complete placement, either a solution or a dead end. Backtracking is like a depth-first explorer who walks down a branch of the tree until it cannot go further, then steps back and tries another branch. The recursive procedure works like this. Place parentheses row close parenthesis colon. If row equals n, then all rows filled comment, record a solution. Return, for each column c from 0 to n-1 colon. If it is safe to put a queen at row comma c parentheses colon, put queen at row comma c call place with row plus 1. Go to next row comment. Remove queen from row comma c backtrack comment. The word recursive means the function calls itself just like a set of Russian dolls, where each smaller doll contains a copy of the whole set inside it. Each call tries to place one queen, and when it succeeds it moves to the next row. If it fails later, it undoes the last move and tries a different column. A placement is safe when the new queen does not share a row, a column, or a diagonal with any queen already on the board. Row check because we place queens row by row, we never put two queens in the same row. Column check, we keep a list call from 0 to n-1, where call of c is true if a queen is already in column c. Diagonal check, two squares are on the same backslash diagonal if row minus call is the same. They are on the same slash diagonal if row plus call is the same. So we keep two more Boolean arrays diag1 from 0 to 2 n-2 for row minus call plus n-1, and diag2 from 0 to 2 n-2 for row plus call. If any of these three arrays already says occupied, we prune cut off that branch right away. This is like a gardener who stops planting a flower in a row that already has a weed, no need to waste time checking further. The worst case number of nodes the algorithm may explore is about n factorial, because for the first row we have n choices, for the second at most n-1, then n-2, and so on. Therefore, the time complexity is big O of n factorial. However, pruning cuts away most branches, so in practice the running time is much smaller. The space complexity is big O of n for the recursion stack plus big O of n for the three helper arrays: column, diagonal 1, diagonal 2. The branching factor at depth k is the number of safe columns in row k, which can be as high as n-k, but often far less because many columns are blocked by earlier queens. Many solutions are just rotations or mirror images of each other. For example, if you rotate a solution 90 degrees, you get another valid solution that looks different, but is essentially the same pattern. By fixing the queen in the first row to be in the first half of the columns, or even fixing it to column 0, we can discard symmetric duplicates. This reduces the amount of work roughly by a factor of 2 for mirror symmetry or 4 for rotation. When we count solutions, we can generate only the canonical ones, and then multiply by the symmetry factor to get the total count. This is similar to counting distinct ways to arrange colored beads on a necklace, where flipping the necklace does not create a new pattern. In code, we usually store the three Boolean arrays call, diag1, diag2 as integers and use bit operations. This is called bit mask optimization. For an n less than or equal to 32 board, we can keep each array in a 32-bit integer. A bit set to 1 means the column or diagonal is occupied. To test safety, we combine the three masks with bitwise OR and check if the bit for the current column is 0. To place a queen, we set the bit using bitwise XOR or OR, and to remove it, we clear the bit using XOR again. This makes the inner loop extremely fast, because a single CPU instruction can test many positions at once. The data structure for the board itself can be a simple array pose of row equals column, which also lets us print the board later. To see how fast the algorithm runs, we measure the wall clock time for different n, for example, n equals 8, 10, 12 through 15. We also count how many recursive calls are made and how many solutions are found. Plotting time versus n shows an exponential curve confirming the big O of n factorial nature. But we also see that the bit mask version can solve n equals 15 in well under 1 second on a laptop, while a naive version may take minutes. Benchmarks are often run on the same hardware with the same compiler flags, and the results are reported in tables like columns n solutions calls time in milliseconds, 892 1200 0.1, 12 14200 100,005, 15 2,279,184, 2,150. These numbers help us compare different implementation tricks: plain recursion versus bit mask, with versus, without symmetry reduction. The classic problem can be tweaked. In a toroidal board, the edges wrap around like a video game screen. Moving off the right edge appears on the left, and moving off the bottom appears on the top. This adds extra diagonal attacks because a queen can attack across the wrap around. The rules change the conflict checks to use modulo arithmetic. Two squares share a toroidal diagonal if row minus col modulo n is equal or row plus col modulo n is equal. The number of solutions is usually much smaller. Another variant is to ask for multiple solutions at once. For example, the first k distinct arrangements or all solutions that satisfy extra constraints like a queen must be on a particular square. The backtracking framework stays the same, we just add more conditions before accepting a solution.